Imagine trying to efficiently heat or cool a massive factory, or maybe move oil thousands of miles through a pipeline without losing too much energy.
Or even just making sure your home radiator works properly.
Right. At the heart of all these systems lies something fundamental, but often invisible: internal forced convection.
It's really the science of how fluids, liquids, or gases move and transfer heat inside confined spaces. Think pipes, ducts, tubes.
And today we're going to take a deep dive into your sources on this. Our mission for you is to really distill the most important insights, maybe uncover some surprising facts, and give you practical takeaways.
Yeah, the goal is for you to walk away with a solid handle on this essential topic without getting totally bogged down in, the really dense details.
So where are we drawing from today?
Our sources are key excerpts from a pretty comprehensive textbook chapter on internal force convection. It gives us that foundational understanding of the principles, the different flow regimes, and the tools engineers actually use.
Okay, so what are we going to unpack? What's the plan?
Well, we'll start with the basics. What makes internal flow different from, say, flow over a wing?
The internal versus external thing. Got it.
Then we'll look at how engineers describe what's happening inside the pipe, the speed, the temperature. That leads us straight into the really critical difference between laminar and turbulent flow.
Smooth versus chaotic, basically.
Exactly. And we'll also explore that entrance region, what happens right when the fluid enters the pipe. It's not instantaneous.
Okay, and then heat transfer.
Yep. The two main ways heat gets transferred under different conditions. And we'll even tackle the, let's say, tricky transitional flow regime.
The in-between stage.
Right. Which can be a real headache for designers. And we'll try to weave in real-world examples all the way through so you can see how these concepts actually play out.
Sounds good. So let's start right there. Internal forced convection. What is internal flow fundamentally, and how is it different from that air flowing over a car example?
Okay, the fundamental difference. It's all about confinement.
Confined.
Yeah. Think about external flow, like air over an airplane wing. The fluid has a free surface, right? And the boundary layer, that thin zone near the surface where the speed changes dramatically, it can just grow outwards, almost indefinitely.
Into all that surrounding air.
Exactly. But with internal flow, the fluid is totally confined by the inner walls of the tube or the duct.
Ah, so the boundary layer can only grow so far before it hits the other side or meets in the middle.
Precisely. That confinement fundamentally limits how much the boundary layer can grow.
And why does that difference matter so much in practice?
Oh, it's absolutely crucial. Think about heating or cooling systems. You're deliberately forcing fluids through long sections of pipe or duct specifically to get the heat transfer you want.
Right, you need that contact time and area.
You do.
Yeah.
And understanding internal flow is key to figuring out really practical things like how much pumping power do I need? Or exactly how long does this tube have to be to heat this water up to 80 degrees?
Okay. Now, I've always wondered about the words pipes, ducts, tubes. Are they basically the same, or do engineers use them differently?
They do have slightly different connotations, though it's not always super strict. Pipes usually suggest circular cross-sections, often for liquids, especially under pressure.
Okay.
Ducts are often non-circular, think rectangular, and typically used for gases like in your HVAC system.
Right, the air ducts.
And tubes are generally just, smaller diameter pipes.
So why are circular pipes so incredibly common? It feels like you see them everywhere.
There's a very good reason. Structurally, their shape is great at handling pressure differences, internal or external, without distorting.
Makes sense. Symmetrical.
Yeah. And here's the big engineering win. For a given amount of surface area inside, a circular tube gives you the most heat transfer for the least amount of pressure drop.
Efficiency.
Exactly. It's a huge advantage for efficiency. That's why they dominate heat transfer equipment. Non-circular ducts, on the other hand, you see them where pressure differences are small and maybe manufacturing cost is a driver, or fitting into tight spaces is more important.
Like those rectangular ducts you mentioned, fitting flat against a ceiling.
Precisely. They can be designed to fit specific architectural constraints, sometimes easier to make from sheet metal or integrate into structures. So for some applications, that outweighs the slight hit on pressure efficiency.
Okay, that clarifies things. But, in the real world, is it all clean equations, or is it messier?
Oh, it's definitely messier. The underlying theory is solid. We understand the physics. But getting perfect analytical solutions for complex real-world pipe systems, that's rare.
So what do engineers do?
They rely heavily on experimental results, on empirical relations, basically, formulas derived from lots and lots of testing.
Learning from what works.
Pretty much. And it's normal to expect, say, 10% error maybe more, in calculations like friction factors. It's less about finding the perfect number and more about designing robust systems that work reliably.
Okay, so inside the pipe, the fluid speed isn't uniform, right? It's 0 at the wall.
The no-slip condition, yeah, the fluid sticks right to the wall.
And fastest in the middle.
Mm-hmm.
And temperature probably varies too. So how do you talk about this practically?
That's where averages come in. They're incredibly useful. We talk about an average velocity, often written as VAVG. It represents the average speed across that whole cross-section.
Okay.
And for incompressible flow like liquids, usually in pipe that doesn't change size, this average velocity actually stays constant as the fluid moves along.
Doesn't speed up or slow down overall.
Right. For instance, in fully developed laminar flow, that smooth layered flow, the average velocity is exactly half the maximum speed you see right in the center.
And temperature. Is it the same idea, an average temperature?
Similar concept, but a key difference. We use a mean temperature to know, which is the average temperature across the section. But unlike the average velocity, the mean temperature changes as the fluid flows along if it's being heated or cooled. But it has to, right? It's gaining or losing energy.
That makes sense. Energy balance. Are there any sort of minor effects we usually ignore but are good to know exist?
Yeah, one is frictional heating. The friction within the fluid actually converts a tiny bit of mechanical energy into heat.
So friction makes it slightly warmer.
Technically, yes.
No?
But the temperature rise is usually so minuscule, it's completely negligible.
Yeah.
You'd only really consider it if you had, say, extremely viscous fluids like heavy oils moving very fast.
So for most things, friction just means pressure drop, not significant heating.
Exactly. Pressure drop is the main consequence you worry about.
Okay. Now for maybe the most fundamental split in how fluids behave inside pipes. Laminar versus turbulent flow. You use the analogy of a calm river versus raging rapids.
It's a great visual. Fluid flow in a tube is fundamentally one or the other. Laminar, smooth, streamlined, orderly layers sliding past each other.
Very predictable.
Yes. And turbulent, chaotic, swirling, intense mixing, very disordered.
And there's a number that tells us which regime we're in.
Yes. The absolute gatekeeper is the Reynolds number. Engineers usually just call it RE.
RE.
It's dimensionless, just a ratio, no units, which makes it universally useful. It basically compares the inertial forces trying to keep the fluid moving to the viscous forces trying to slow it down.
How do you calculate it?
For a standard circular tube, it's the average velocity times the diameter, divided by the kinematic viscosity of the fluid.
Okay.
For non-circular tubes, you swap out the diameter for something called a hydraulic diameter, which is a way to account for the different shape.
So what are the magic RE numbers? Where's the dividing line?
Well, the general rule of thumb is below about 2300, the flow is considered laminar.
Okay, below 2300, smooth flow.
Above roughly 10,000, it's generally fully turbulent, lots of mixing.
And the gap in between.
That's the transitional regime, from about 2300 up to 10,000. Here, the flow is unstable, kind of flickering between laminar and turbulent states. It's messy.
Which one is more common in practice?
Turbulent, by far. Most industrial applications involve higher velocities to move fluids effectively or enhance heat transfer, and that pushes the Reynolds number well into the turbulent range.
Now, here's something that jumped out at me from the sources. We learn 2300 is the limit for laminar flow, but then it mentions laminar flow being maintained up to RE of 100,000.
I know. Isn't that amazing?
That's almost 50 times the usual limit. How is that even possible? It sort of blew my mind.
It really highlights that 2300 isn't some absolute law of physics. It's more of a practical threshold for typical conditions. In incredibly smooth pipes, with extreme care taken to eliminate any vibration or disturbance at the inlet.
Like laboratory conditions?
Exactly. Under those pristine conditions, you can coax the fluid to remain laminar at Reynolds numbers that seem impossibly high. It just shows how sensitive that transition is to tiny disturbances. Nature's rules are often more subtle than our engineering rules of thumb.
That's a fantastic insight. Okay, let's move to the pipe entrance. You said the flow doesn't just instantly adopt its final pattern. There's this developing phase. What's going on there?
Right. So fluid enters the pipe. Immediately, the no-slip condition at the wall means the fluid right at the wall stops. This creates friction, slowing down adjacent layers.
Like brakes applied at the edges?
Kind of. This region of changing velocity growing inwards from the wall is the velocity boundary layer.
And it gets thicker as the fluid moves down the pipe?
Initially, yes. And because the fluid near the walls is slowing down, to maintain the same overall mass flow rate through the pipe, the fluid in the central core actually has to accelerate.
Oh, interesting. So the middle speeds up to compensate for the edges slowing down.
Correct. This whole section where the velocity profile is changing and hasn't reached its final stable shape is the hydrodynamic entrance region.
Hydrodynamic. Okay. And if heat is being transferred too.
Same idea, but for temperature. If the wall temperature is different from the fluid temperature, a thermal boundary layer develops.
Where the temperature changes from the wall value to the bulk fluid value.
Exactly. And that also grows until the temperature profile, we usually look at it in a dimensionless form, becomes stable. That stretch is the thermal entrance region.
So you need both velocity and temperature profiles to stabilize.
Yes. Once both the velocity profile and the dimensionless temperature profile stop changing along the length of the tube, you've reached the fully developed flow region.
And what's special about that region?
That's where things become simpler, in a way. The local friction factor, a measure of flow resistance, becomes constant. And the local heat transfer coefficient also becomes constant.
Okay, stable conditions. How long are these entrance regions? Are they short, long?
It depends massively on whether the flow is laminar or turbulent.
Ah, back to RE.
Yep. For laminar flow, these lengths can be surprisingly long. The hydrodynamic entry length is roughly 0.05 times the Reynolds number times the diameter.
So it scales with RE.
It does. And the thermal entry length is related to that by the Prandtl number, another dimensionless number. So laminar entry lengths can be significant.
But for turbulent flow, you said it mixes things up quickly.
Much, much shorter. Because of all that chaotic mixing, both the hydrodynamic and thermal entry lengths in turbulent flow are roughly just 10 times the pipe diameter.
Wow, only 10 diameters. That's a huge difference. Turbulent flow develops way faster.
A crucial difference, yeah. It gets to that fully developed state very quickly.
You mentioned the Prandtl number connecting the thermal and hydrodynamic lengths. Can you unpack that a bit more? What does the Prandtl number actually tell us?
Right, the Prandtl number, or PR. It's really neat. It's a fluid property, a ratio that tells you how quickly momentum diffuses compared to how quickly heat diffuses in that specific fluid.
Momentum versus heat diffusion.
Basically, yes. It tells you about the relative thickness or growth rate of the velocity boundary layer compared to the thermal boundary layer.
So what does a high or low PR mean?
Okay, for gases, PR is usually around 1. That means momentum and heat diffuse at similar rates, so the velocity and thermal boundary layers grow roughly together.
Makes sense.
But for oils, PR is very high, maybe hundreds or thousands. This means momentum diffuses much faster than heat. So the velocity boundary layer develops much faster, it grows quicker than the thermal boundary layer, the hydrodynamic entrance length is shorter than the thermal one.
I see. Velocity profile stabilizes before the temperature profile.
Exactly. And the opposite is true for liquid metals like sodium or mercury. They have very low PR, much less than 1. Heat diffuses incredibly fast, much faster than momentum.
So the thermal boundary layer outruns the velocity one.
You got it. The thermal profile develops much more quickly. LT is shorter than LH. It's quite fascinating how different fluids behave.
It really is. So what are the practical consequences of this entrance region? Why does an engineer need to worry about it?
The big takeaway is this. Right at the inlet, where those boundary layers are super thin, the friction against the wall shear stress, is highest.
More drag right at the start.
Yes. And similarly, the heat transfer coefficient is also highest right at the inlet.
Better heat transfer initially.
Correct. Both friction and heat transfer rates gradually decrease as the flow develops and the boundary layers thicken. So that entrance region actually boosts the average friction and the average heat transfer for the whole tube.
Ah, so it's not insignificant.
Not for short tubes. The effect can be quite large. For very, very long tubes, the entrance region is just a small fraction of the total length, so its effect becomes negligible compared to the long, fully developed section. But for heat exchangers with shorter tubes, you absolutely have to account for that enhancement.
Okay, that's clear. Now let's talk about the heat transfer itself inside the tubes. The sources highlight two main scenarios. What are they?
The two main thermal boundary conditions engineers typically analyze are: 1, constant surface heat flux.
Meaning heat is added at a steady rate all along the tube.
Exactly. Think of an electric resistance heater wrapped around the pipe, or maybe uniform radiation hitting it. Heat is supplied evenly per unit area.
And what happens to the fluid temperature then?
The mean fluid temperature inside just increases linearly as it flows down the tube. Nice and simple. And in the fully developed region, the actual surface temperature of the tube will also increase linearly, staying a constant amount hotter than the fluid.
Okay, linear increase. What's the second scenario?
The second one is constant surface temperature, often written as T's equals constant.
Where would that happen?
A common example is if there's a phase change happening on the outside of the tube. like steam condensing or refrigerant boiling. That phase change process tends to keep the wall temperature very steady and uniform.
Okay, constant wall temperature. Now, for this case, the sources really emphasize something called the log mean temperature difference, or LMTD. Why is that so critical?
Ah, yes, delta TLM. It's vital because in this constant wall temperature case, the fluid temperature doesn't rise linearly anymore.
How does it change then?
It approaches the wall temperature asymptotically. Think of a curve that starts rising quickly but then levels off as it gets closer and closer to the wall temperature.
Okay, an exponential-like approach.
Exactly. Now, you might think, why not just average the temperature difference at the inlet and the outlet? That's the arithmetic mean.
Seems intuitive.
It does, but it's often wrong. Because the temperature change isn't linear, that simple average doesn't accurately represent the true average driving force for heat transfer over the whole tube length.
And the log mean temperature difference is the accurate way.
It is the mathematically exact average temperature difference for this scenario. The sources are really clear. Using the simple arithmetic average can lead to huge errors. They cited one example where the calculated pipe length was off by 70%.
70%. Wow. So rule is always use LMTD for constant surface temperature.
Pretty much always. The only exception is if the temperature difference at the inlet and the outlet are very, very close, say, they differ by less than 40%. Then the arithmetic mean is a decent approximation. Otherwise, delta TLM is essential. Getting it wrong is a major design pitfall.
Good warning. What about this other term, the number of transfer units, or NTU? How does that fit in?
NTU is another useful dimensionless parameter. It's basically a measure of the heat transfer size or effectiveness of the heat exchanger, relating the heat transfer capacity, coefficient times area, to the fluid's capacity to absorb heat. Mass flow rate times specific heat.
What does a high or low NTU tell you?
A high NTU, maybe 5 or more, means the heat exchanger is very effective. The fluid outlet temperature gets very close to the surface temperature. You basically extracted almost all the heat you possibly can.
So making the tube even longer wouldn't help much.
Exactly. You've hit diminishing returns. A low NTU, on the other hand, means there's still plenty of potential for more heat transfer if you made the tube longer or increase the heat transfer area.
So NTU helps in optimizing the design, balancing performance and cost?
Precisely. It's a key factor in deciding how big to make the heat exchanger to achieve the desired performance without excessive cost.
Let's zoom in on laminar flow again. You said the velocity profile is parabolic. Can you describe that a bit more?
Sure. Imagine the cross-section of the pipe. Velocity is 0 right at the wall. As you move towards the center, it increases smoothly, following a parabolic curve, reaching its maximum value right at the exact center of the pipe.
Perfectly symmetrical.
Yes. And as we mentioned, the average velocity across that whole section is exactly half of that peak velocity in the center.
Okay. Now, pressure drop. The sources mentioned Poiseuille's law and something pretty dramatic about pipe diameter.
Yes. For laminar flow, the pressure drop needed to push the fluid through is proportional to the fluid's viscosity and the pipe length. Makes sense. Longer pipe, more friction.
Right.
And it's inversely proportional to the diameter squared. But here's the really striking part. Poiseuille's law relates to the volume flow rate for a given pressure drop. The volume flow rate you get is inversely proportional to the diameter of the fourth power, d to the 4.
Fourth power. Seriously, what does that mean practically?
It means if you double the pipe diameter, keeping everything else the same, you can get the same flow rate with only 1/16 the pressure drop. Or, for the same pressure drop, you get 16 times the flow.
1/16 the pumping power. That's incredible leverage.
It's huge. A massive consideration in design.
But wait, if doubling the diameter cuts pumping power so drastically, why aren't all our pipes enormous? What's the catch? There must be trade-offs.
Yeah, absolutely. It's classic engineering compromise. That huge energy saving comes at the cost of, well, a much bigger pipe.
Which costs more to make and install.
Exactly. Significantly higher material costs, installation costs. A larger pipe also holds more fluid, which increases the residence time, how long the fluid takes to get through. That might matter for process control or response times.
And space. Bigger pipes take up more room.
Definitely. Space constraints are often critical. So engineers have to balance those huge potential energy savings from the d to the 4th relationship against the initial capital costs, the space limitations, and maybe the process dynamics. It's rarely a simple choice.
Okay, that makes sense. What about the friction factor in laminar flow? You said it was simple.
It is remarkably simple for laminar flow in a standard circular tube. The friction factor, F, is just 64 divided by the Reynolds number. F equals 64 air.
That's it.
That's it. And crucially, notice what's not in that equation. Surface roughness.
Ah, you mentioned that. Roughness doesn't matter for laminar flow friction.
Correct. The fluid flows in such smooth, orderly layers that the tiny bumps and imperfections on the pipe wall don't really disturb it enough to increase the overall friction significantly.
Interesting. How about heat transfer in laminar flow, the Nusselt numbers? You hinted they were sensitive to how heat is applied.
Yes, this is a key point for laminar flow. The Nusselt number, nu, which represents the heat transfer effectiveness, is different depending on the thermal boundary condition.
The constant heat flux versus constant temperature cases.
Exactly. For constant surface heat flux, the fully developed Nusselt number is a constant, 4.36. For constant surface temperature, it's also constant, but lower, 3.66.
So about 16–17% difference.
Right. The main insight isn't the exact numbers, but that laminar flow heat transfer is noticeably sensitive to the type of boundary condition. Constant heat flux gives you better heat transfer.
So a designer might prefer constant heat flux if they want higher heat transfer efficiency in a laminar system.
They might, if they have control over how the heat is supplied. It means you could potentially achieve the same amount of heating with a smaller, maybe cheaper heat exchanger just by choosing the boundary condition carefully. That's a powerful lever.
There was that oil pipeline example in the sources,
Yeah.
example 8-3. What did that show about viscous fluids?
That example really drove home the point about entry lengths for high Prandtl number fluids.
Well,
Oil is very viscous, high PR. The calculations showed that the thermal entry length could be incredibly long, like over 100 kilometers calculated for just a 200-meter actual pipe section in the example.
Wow, so the temperature profile basically never reaches that fully developed state in any practical length of pipe.
Pretty much. For practical purposes, the flow is always thermally developing. You simply can't use the simple, fully developed Nusselt numbers like 3.6 or 4.36. You have to use correlations specifically designed for the thermal entrance region.
And those give different results.
Yes, they typically predict much higher heat transfer coefficients than the fully developed values because the thermal boundary layer is still relatively thin over much of the pipe length. Ignoring the entrance effect would lead to significantly underestimating the heat transfer.
Got it. So laminar flow has these specific characteristics, but you said turbulent flow is often preferred in engineering. Why again?
Mainly because of the significantly higher heat transfer coefficients. That chaotic mixing in turbulent flow is just much, much better at transferring heat between the wall and the bulk of the fluid.
More efficient heat transfer.
Way more efficient, generally.
And is turbulent flow well described by theory, or is it more about experiments?
It's largely an empirical game. Because it's so chaotic and complex, purely theoretical solutions are extremely difficult. So most of the tools engineers use the correlations for friction factor and Nusselt number are based on vast amounts of experimental data.
Like recipes based on testing?
Exactly. Equations like the Dittus-Bolter or the Nielinski correlation are workhorse empirical formulas used to predict heat transfer in turbulent flow.
How does surface roughness affect turbulent flow? You said it didn't matter much for laminar.
But for turbulent flow, it's a huge factor. Unlike laminar flow, the friction factor in turbulent flow is a strong function of the relative roughness of the pipe surface.
Rougher pipe means more friction.
Definitely. Those little bumps and imperfections stick out into the turbulent flow near the wall, disrupting it and causing significantly more drag, which means a higher pressure drop. Engineers use tools like the Moody chart, or equations like the Colebrook equation, or it's easier to use approximations like the Haaland equation, to account for roughness.
Okay, roughness matters a lot in turbulent flow. What about the Nusselt numbers for heat transfer? Are they sensitive to constant heat flux versus constant temperature, like in laminar flow?
Thankfully, no. That's one area where turbulent flow is actually a bit simpler for analysis. The Nusselt number correlations for turbulent flow are generally not very sensitive to whether you have constant wall temperature or constant heat flux.
So you can often use the same correlation for either case.
Pretty much, or the difference is small enough to ignore in many practical calculations. There are specific correlations for different ranges of Reynolds and Prandtl numbers, including special cases like liquid metals with their very low Prandtl numbers.
It sounds like engineers are always trying to squeeze out more heat transfer. What techniques are used to actively enhance it?
Oh, lots of clever techniques. You can intentionally roughen the surface or add ribs, corrugations, or fins inside the tube.
To trip up the flow and increase mixing.
Exactly. These passive techniques can boost heat transfer by, say, 400% or even more. But there's no free lunch.
Ah, the trade-off, more friction.
Yep. Significantly higher pressure drop and therefore higher pumping power needed. It's always a balance. Other methods include things like pulsating the flow or coiling the tube to induce a swirling motion, which also enhances mixing and heat transfer.
Interesting. And the example of heating water, example 8 to 5, what did that illustrate?
That showed a practical calculation, figuring out the required heat or power rating, and, importantly, the temperature of the inner surface of the tube.
Why is the inner surface temperature important?
Because it can be significantly hotter than the average fluid temperature, especially with high heat fluxes. You need to make sure the pipe material can handle that temperature without failing. And as another example showed, you also need to consider the outer surface temperature for safety, maybe adding insulation.
Right, preventing burns. Okay, this leads us nicely into that challenging transitional flow regime, RE between roughly 2,300 and 10,000. Why is it so tricky?
It's tricky because it's inherently unstable and unpredictable. The flow is constantly oscillating, switching back and forth between behaving like laminar flow and behaving like turbulent flow.
Making it hard to model accurately.
Very hard. The friction factors and heat transfer coefficients can fluctuate significantly and are highly sensitive to exact conditions. Engineers generally try to design systems to operate squarely in the laminar or fully turbulent regimes if possible, just to avoid this unpredictable zone. But sometimes, constraints force you to operate there.
The sources mention that the inlet geometry, how the fluid enters, really affects this transition. Can you elaborate?
Yeah, the shape of the inlet matters a lot. A sharp-edged or entrant inlet, where the pipe sticks into the reservoir, creates more disturbance right at the start, which tends to trigger the transition to turbulence at a lower Reynolds number.
Pushes it towards turbulence sooner.
Right. Conversely, a very smooth, rounded bell mouth inlet introduces the fluid very gently. This can actually delay the transition, allowing laminar-like flow to persist to higher Reynolds numbers, sometimes well into the usual transitional range.
So the same RE could be transitional with one inlet, but still laminar-like with another.
Potentially, yes, especially near that lower bound, around 2,300, 4,000. Even factors like heating the fluid can influence where the transition actually occurs. It's complex.
What about smaller scale systems like mini or microtubes? Is transitional flow different there?
There's evidence it can be. The transition range sometimes seems to narrow as the diameter gets really small. And in specialized tubes, like the microfin tubes used in air conditioners to enhance heat transfer.
You mentioned those.
Right. In those, the internal fins create so much extra turbulence and mixing that the whole concept of a clear transition regime changes. The friction and heat transfer behave differently across a wider range of Reynolds numbers compared to a smooth tube. The angle of those spiral fins plays a big role, too.
We saw a comparison in example 8.6, turbulent versus transitional. What was the key takeaway?
That example was stark. Same basic setup, but lowering the flow rate pushed the system from turbulent into transitional flow. The result, the heat transfer coefficient dropped dramatically.
Much worse heat transfer.
Yes. And because the heat input was the same, the inner surface of the tube got significantly hotter. It really underscores the danger. If you design assuming turbulent flow but actually end up in transitional, your system could overheat or perform very poorly. Understanding the regime is critical for safety and efficiency.
In example 8 to 7 directly applied this to safety, calculating insulation thickness.
Exactly. A direct application using the heat transfer calculations, accounting for the flow regime, to ensure the outside of a hot pipe isn't a burn hazard. Very practical.
Finally, examples 8.9 and 8.10 really hammered home the inlet type importance. What did they show?
They showed explicitly how, at the exact same Reynolds number, you could have fully developed turbulent flow characteristics if you had a sharp, square-edged inlet.
Because it trips the flow early.
Right. But with a smooth bell mouth inlet at that same Reynolds number, the flow might still be in the unpredictable transitional region, or at least behaving differently.
Leading to different heat transfer.
Yes, potentially quite different performance. The bell mouth case, for instance, sometimes shows an odd dip in heat transfer partway down the tube as the flow slowly evolves. These subtle differences caused by inlet geometry are things engineers absolutely need to be aware of to avoid nasty surprises in performance.
Okay, so wrapping this up, what does this deep dive mean for you, our listener? We've journeyed through internal forced convection, from the basic differences with external flow, through laminar, turbulent, and that tricky transitional zone.
Hopefully, you now have a much clearer picture of how engineers analyze these systems, thinking about average velocities, mean temperatures, the crucial Reynolds number, entry effects, and those key boundary conditions like constant heat flux or temperature.
It really makes you think, doesn't it? Consider the water pipes in your house or the air ducts overhead. What flow regime do you reckon they operate in? Probably turbulent most of the time for main lines, maybe laminar in smaller branches.
Could be. And thinking about these principles, how could understanding them help design better systems,
Hmm.
more efficient heating, say for industrial processes, maybe even spotting energy waste?
And here's a final thought to ponder. We talked about that incredible D to the fourth power relationship for pumping power in laminar flow.
The Bouzois law effect, yeah.
How might that fundamental principle, where diameter has such an outsized impact, influence design in completely different fields? Think about, say, biomedical engineering, designing artificial capillaries or microfluidic devices. How critical would understanding that relationship be when dealing with flow in tiny channels where efficiency, whether biological or device related, is absolutely paramount?
That's a great question. Balancing flow rate, pressure drop, and device size at those scales. It brings these principles into a whole new context.